All right, so just to recap a little bit. So we talked about the access mechanism for Wi-Fi in the simplest case. So a transfer starts with a diffs being idle on the channel. A data frame is transmitted, one waits for a SIFS, and then one expects an ACK to be received within, start to be transmitted within a SIFS. And once it's finished, one starts all over again one waits for a diffs, and then we go into back off. Okay. So the only time we start to transmit immediately after a diffs is when we get the first frame. So what is the first frame? Well, obviously one frame is the first, but then after a while we don't have any frames to transmit, and then after a while we repeat and think of the frame that comes after that as being the first frame. But this could be a first frame, for instance, for sure. But if one measures the channel and finds it to be busy, then we have to wait until the current transmissions is over and then do back off until we can start to transmit a frame. Okay. Any questions on this? Okay. So this back off procedure, if we go into more detail about that, so we wait a random time, and it's the backup period is a random integer times we wait for a random number of idle contention time slots. So during when we count down a back slot, when we count down the back off timer here, we go from R equal 6, 5, 4, 3, 2, 1, 2, 3, 4, 6, 5, 4, 3. No. I think it's like this. 6, 5, 4, 3, 2. So, no, it was correct. Okay. 6, 5, 4, 3, 2, 1, 0. Okay. So the transition from the backoff counter is at the border between two backoff slots, and we can only count down if the channel has been idle during the slot. As soon as it becomes busy, then we pause the backoff. Okay. Okay. So we decrement the backoff counter after an idle slot. Backoff stops when the medium becomes busy, and resumes after a diffs of idle medium. Okay. And then we transmit when the backoff counter reaches 0. Okay. Now, so how do we select this backoff counter? Well, we select the backoff counter R in this interval from 0 to CW, where 0 and CW are integers. So the CW, the upper limit of the contention window, this is known as the contention window. It varies from a minimum value to a maximum value. Okay, so, and the minimum value the minimum and maximum value depends a little bit on the version of, or the type of Wi-Fi access we use. So depends on certain parameters. So for 802.11 with 20 megahertz channel spacing, then the minimum contention window size is 15, and it maximizes at 1023. Okay, and so this contention window, it varies in size. Almost, if you remember this binary exponential backoff we had in Ethernet, where the possible values the back-off counter could take on increases with the number of collisions, consecutive collisions. So here's the same thing. So we get retransmissions. And when do we get retransmissions? Well, it's when we don't receive an ACK after our transmission. And if you remember, so how this was set up, then the ACK after a data frame needs to arrive after a CIFS. Okay, it needs to start to arrive after a CIFS. If it hasn't arrived here, we know it's going to be lost. Okay, so the timeout here that we typically have in these stop and wait type of protocols is that we have a turnaround time, but here the turnaround time is determined by the protocol to be a CIFS plus the length of an ACK frame. So at this point in time, if the ACK frame has been lost, say, so if the ACK frame has been lost or not received, then the source needs to know, will trigger a retransmission. Okay, at this point in time. Okay. So retransmissions are triggered when ACKs are lost. And for each new retransmission try, we basically double the contention window size. So we start at say we start at 15, and the next time it's 2 times 15 plus 1, which is 31. Now next time is 2 times 31 plus 1, which is 63, I guess. 127 and up so until we reach 1023, and then it's 1023 for any retransmissions after that. Now, if a transmission is successful, then we go back to 15 again. So for the next frame, if it's lost, then we start at 15 again. And the reason for this is that we would like to make the contention window as small as possible to avoid delays, but we want to make it big enough so that we can handle randomization between different nodes trying to access the channel at the same time. So for Wi-Fi and wireless in general, these collisions are very costly. So one tries to avoid them if one can. Costly in time, so in terms of time, which then translates into throughput. Okay, so this carrier sensing, actually 2 ways we do carrier sensing in Wi-Fi. Either physically, like physical carrier sensing that we have talked about earlier. One basically listens to the channel and monitor the received power on it. Does it look like the channel is busy or not? But then there is also something called virtual carrier sensing, and this is done at the MAC layer by receiving a frame and then looking into the header of that frame. Then there is a duration field in that frame that tells us, okay, this frame plus its ACK will take this many microseconds to complete. Okay, and then a node that has decoded this can then simply start a counter and then wait. Okay, so it works like this. So the source station, the one which is transmitting its frame, informs other stations about the duration of the transmission in microseconds for the MAC, PDU plus the ACK if it's applicable, if we have ACKs, which we normally do. The transmission duration is found in this duration field. We will see ahead a little bit later. And stations that can decode this frame can then maintain a timer, and this timer is called, for some odd reason, it's called the network allocation vector, or NAV, this timer, to indicate when the channel becomes idle after the current transmission. So a channel is declared busy if either it's physically sensed as being busy or virtually sensed as being busy. Okay. One of the good things about this virtual carrier sensing is that if I'm a node who would like to transmit, I listen to the channel and I see, okay, there is a frame coming here. I look in that header, I see that there is, okay, it will take you 500 microseconds before the channel becomes possibly idle again. Then what I can do is I can start a timer and go to sleep for 500 microseconds, and thereby saving a little bit of battery. Okay, so it's good for power saving, if nothing else. This. Okay, so how this works, virtual carrier sensing, is that we start again transmitting a data frame here. Now, every other node who hears this data frame, which is ongoing, can decode it and look into the header and figure out the nav field, and then basically go to sleep for this. Or if it doesn't hear the ACK frame, if it doesn't hear the data frame, it can also hear the ACK frame. There is a duration field in here also, which can be decoded, and we can be go to sleep there. So these are virtual carrier sensing. Of course, one can measure also the received power during this time, and then if we're unable to decode the frame, but we hear there is a power on the channel, then we can wait, but then we're a little bit unsure how long this will take, and then we have to measure the channel until we get to this point, and a little bit of sieves, and then this power and so forth. So virtual carrier sensing is more efficient if we can do it. And we can do it if the data frame is sufficiently strong at the receiver. So the received power is sufficiently strong. Okay, and then we back off. So any question on this virtual carrier sensing? No? Okay. So what could possibly go wrong here? Well, there are several things. As we said earlier, due to this decay of power as we go in distance, it's not sure that by listening to the channel that you hear all the frame transmission which are ongoing at the same time. So if we have a situation like this, where we have an access point in the middle, and we have a laptop to the left and a laptop to the right, then if A transmits a data frame, it's not sure that C would be able to detect it, because the received power here at C is much lower than the received power at the access point. And maybe the laptop here is just at the border, so it can reach the access point but no further. Meaning that the received power here is enough to detect the data frame, but the received power here is not enough to detect the data frame. Remember that the power decreases as we go with distance. So station C here, if it has a frame also to transmit, it will sense the medium, but will not hear A. Okay. And then we say that station A is hidden from C. Okay. Station A, its activity cannot be sensed by station C. So A is hidden to C. Then C can then, of course, start to transmit its data frame, say, that it would like to reach to the access point, and then we have a collision here, and probably both frames are lost. Okay. So this is known as the hidden terminal problem, when carrier sensing does not work. When the received power at the device who do the carrier sensing is weak, too weak for it to detect it, the communication ongoing. So was that reasonably clear? So what do we do about this? Well, there is a mechanism in 802.11 to reduce the probability for this, and that's called an RTS-CTS handshake. So RTS stands for request to send, and CTS stands for clear to send. So it works something like this, that if A has a frame to transmit, it transmits a small packet called an RTS to the access point saying, hey, I have some data, would it be okay to transmit this data? Request to send is that message. The access point say, if it's ready, it says, okay, clear to send, and send that to A here. So request to send, clear to send. So now A knows that it's okay for it to transmit. But we also see that when B is transmitting, the access point here is sending a clear to send to A, that will also reach C. Okay, because C is in range of the access point. C is not in range of A, but it's in range of the access point. So then C knows that the transmission is imminent, will take place now, because somebody else got the clear to send, so it will remain quiet. And then A can transmit this data frame, and there will be no condition. So this is it's known as the RTS-CTS handshake. And as it's seen here, it eliminates the probability for collision due to hidden terminals. But do you see what the problem is? Maybe you already did.
Yeah, perhaps if A and C send an RTS at the same time.
Very good. So how about if there came an RTS here also? That could definitely happen, right? What happens then is that there will be no CTS, because the RTS frames will be colliding here. So if there is not a CTS coming back, then C here would, okay, there was a collision of RTSs here, and it will back off. And B will not receive its CTS, and it will also go into back off. Okay. Just as it would have done if these were data frames. The advantage is that the RTS and the CTS frames are much, much shorter than a regular data frame, which means that this collision destroyed a smaller portion of time than a collision of data frames would do. Okay, so that's the advantage of this. So in a timing diagram, it would look something like this. There is a diffs, there is an RTS, and then everyone else who hears this RTS will read off his duration field and go to sleep or do something else. After a CIFS, there should be CTS returning. Everybody who can hear the CTS go into sleep or defer access by reading the duration field in the CTS. And then there is a CIFS, and then data is transmitted. Everybody who hears the data will go into sleep also. CIFS, ACK, and diffs, and now back off. Okay. So everything is the same except as before, except that we have this thing. Sorry, I should draw that more carefully. This is the extra time required for the CTS RTS handshake compared to what we did previously, where we did not have this. We simply wait for diffs and then transmitted the data. And the advantage, there is an advantage when this is much smaller than the data frame. Okay. However, in practical implementations, I think this is almost never used. Okay, so it seemed to be a good idea, and you read about them in the books, but as far as I know, it's not used in practice. Okay. Yeah, and then there is back off. There is another problem also that has to do with power, and that's called the exposed terminal problem. And here we have a station that is transmitting to an access point, and this signal is then also heard by another station and another access point. This power could be large enough in order for station number 2 here to detect that a frame is ongoing, and therefore it should defer its access. This is typically what we want. But, okay, and this thing is interference to the access point here. But now, suppose that station 2 anyway is transmitted to its access point. Then the power from this transmission over to this access point might actually be weak compared to the power from the station number 1. So access point number 1 would like to get data from station 1. Okay. This interference here is bad for access point 1. But if this interference is weak compared to this, then it can still decode the frame. Okay. So collisions are not always disastrous. Okay. It very much depends on the ratio between the power of the frame that we're trying to decode divided by the power of the frame which is interfering with us. Okay. So for sure, this could be good enough for detecting the frame from station 1. And if that is the case, then there was no need to block station number 2. Okay. So this is unnecessary. And from symmetry, it could be that station 2's transmission could also be decodable at access point number 2, because the interference from station number 1 would be weak. So we can have a situation here when 2 nodes are actually able to transmit at the same time without interfering with each other too much. Okay. And this typically occurs when there is like a wall or something in between here. And there is enough power going through this to block this station, but there's not enough power to destroy the reception at this point. This problem of unnecessary blocking is called the exposed terminal problem. And this is quite real in dense deployments, like in office buildings and so forth. So one is trying to do something about that in current standards here. Okay, any questions about this? Okay, so we have the hidden terminal problem that we basically could do something about with RTS, CTS. Now in practice it's not done. The exposed terminal problem, I have not explained what one can do about that. It's a little bit out of scope for this course, but this is something one definitely is looking at. Frame types. We transmit frames. So data frames we already talked about, but then there is also management frames and control frames. So management frames is for association and disassociation, timing, synchronization, authentication, and de-authentication. We talked about this earlier. So these are frames which are carries no user data, but it's just to organize the network and so forth. We have the control frames, which is the RTS, CTS frames and the acknowledgements. And these are necessary parts of the transmission of user data. And then we have data frames, which actually carries the data. If we look at the frame structure, it looks something like this. This is very complicated, so we're not going to go into many details here. But there are many things needed in the header for this to work. So remember that the frame body here is an LLC PDU. So this is an LLC PDU or a MAC service data unit like this. We see it can be from 0 byte to 2,312 bytes. So if you remember an Ethernet frame, remember how many bytes it could carry? Exactly, 1,500 bytes. So this is a quite much longer maximum length of this compared to an Ethernet frame. But otherwise there is a CRC, just as in the Ethernet frame. And the header looks quite different from Ethernet. It has many fields. For instance, it has 4 address fields here, which is a little bit interesting, so we will talk about that. And then in the frame control here, there's a bunch of things here that we will talk a few of these things in a second. The CRC here is a 32-bit CRC. And it covers both the MAC header and the frame body. So this is used then for error detection. So a receiver would check the CRC. If the frame is in error, it will throw it away, will not send an acknowledgement, and that frame will be retransmitted a little bit later. Okay. So it's like stop and wait ARQ here. we have these multiple address fields. We'll talk about that in a second. And the meaning of these address fields are dependent on these to DS and from DS flags. So let's look into this. So again, in the frame header, we have 4 address fields here: address 1, 2, 3, and 4. And then we have 2 control bits, to DS and from DS. So first of all, when we have communication, we have a transmitter device, which is actually transmitting the signal. And then we have a receiver device, which is picking up the signal. Okay. However, the frame, which is transmitted here, might not be originated from the transmitter. It might have come from some other node on to the left here. And that's called the source node. It's the station that generated the frame payload. And also the receiver might not be the final destination for that frame. So then we have a destination, which are the stations that will process the frame payload. So this hopefully will become clear when we do an example here. So suppose we have a station A that would like to transmits a frame directly to station B. Then this frame is not going to the distribution system, and it doesn't come from the distribution system. So we can think of 2 distribution system is a 1 when the frame is going to an access point, and from is when the signal comes from a access point. Anyways, when it's from A to B here, then the first address is the receiving device, which is B. Okay. The second address is the transmit device, which is station A here. Okay. And then the third address here is the basic service set ID. Okay. So that is, if you remember, the basic service ID is the MAC address of the access point to which we are associated with. Now, in this case, actually the access point is not involved in the transmission, but the receiving device needs to know that, okay, so we are both part of the same BSS ID. Otherwise, we're saying we're part of the same BSS. Otherwise, that frame will not be processed. Okay. Then, if we have, instead of going from an access point 1 to station B, then this transmit device is now an access point, which means that the from DS flag is 1. And then the interpretation of the addresses is here, that B is still the receiving device. Now the access point 1 is the sending device, so we have access point 1 here. Now the access point is never the final, or very seldom the final destination of the frame. So the frame goes from station A to the access point, but after the access point it needs to go somewhere else, namely to the sorry, my bad. We're going from the access point to the station. So we're going from the access point to a station, but the frame that the access point is sending to the station is not originated from the access point. The access point doesn't create frames typically. So it needs to inform the receiver, that is station B, of from what station the frame originated from. Okay. So the green part here. All right. So with 2 more things here. So if we go from station A to the access point, then we are going to an access point. Therefore, 2DS is 1. But we are not going from an access point, so that's 0. Now, then we have here the receiving address is access point 1, the transmitting device is station A, and then that frame which we were transmitting from station A to the access point need to go somewhere, and we need to define that address here. And the final one is when we go from one access point to another access point, then both of these flags will be 1, and then we have address access point 2, access point 1, we have a destination for the frame and a source for the frame, like this. So these are the 4 possibilities. Looking at in pictures instead, if we are transmitting from station A to station B, then we have an address B. This is the address number 1. Address number 2 is A, and then we have the BSS ID here. So it goes from this station. It was generated at, the LLC at this station gave us a frame, and that should go up to the LLC layer at this station, like this. So it goes like this. If we're transmitting from an access point to a station here, then in this case, the LLC layer that originated the frame was located in node A. Okay. Somehow that frame ended up in the access point here through the distribution system, and now it's about to be transmitted down via Wi-Fi down to station B here. So then the destination should be B, that's the receiving device. The transmitting device is the access point, but that frame did not come from the access point originally. It came from the LLC layer in station A, so A needs to be in here. So when this frame is then delivered up to the LLC layer here, it will have destination B and source A, and then LLC PDU here, like this. Okay, so this A here needs to be here because of this LLC layer knowing from where this PDU came from. It doesn't care that it came from the access point. Was this reasonably clear? Remember that the LLC layer here would like to talk to the LLC layer here by sending PDUs. And in that, it would like to know what the source and destination is. These protocols. Okay, and then the opposite, when it comes from A and goes to the access point, then we need to tell the access point what is the final destination of this frame, which is B, like eventually. So then we need 3 addresses here. It goes from it goes to the access point, comes from station A, but this frame should eventually be handed over to B. So that's why we need 3 here. And then finally, we have a situation like this, where we have 2 access points and they are transmitting to each other over a wireless distribution system. So here we can think of these as being, say, Ethernet, but here it could be also over Wi-Fi. You remember, you've probably seen this, that you have routers that can communicate with access points that can communicate with each other wirelessly. So if you have not enough cabling at home or whatnot. Anyways, in this case, we need 4 addresses. We need the receiving access point, the transmitting access point, but the frame which is transmitted here comes from a station A and should be delivered to station B. So that's why we need 4 addresses in this case. Any questions on this? You just look at it and after a while it makes sense. Okay, physical layers then. So remember that we had the link layer, LLC link layer, control layer, and then we have the MAC layer, and then we have the physical layer. So we have many physical layers actually under .11. I don't know, 5 different maybe. So actually there are 2 steps in this physical layer. One which is, convergence procedure, which basically add some bits to this in a way. I will not go into detail here. And then there is actually the physical layer here. So 822.11 is designed to support LSE and to work over many physical layers. And for each physical layer, there is a special middle layer here, which is called this convergence procedure. So before we go into this, if you remember what we did early in the lecture here, I showed you a screenshot from my laptop. So we talked about the SSID, the secure, the basic service ID. So all of these are sort of like network things. Here, this is related to the physical layer. First of all, the country code is important because certain transmit powers and channels are allowed in different regions. So we might have different transmit power constraints for different countries. So in this case, it was configured to work in Sweden. What you can do is that, which is not allowed, but what you can do is to look out, okay, which of the different countries have different channels allowed and different powers allowed, and you can choose one which is beneficial for you, right? By misconfiguration of your access point, which is not allowed, but this is something one can do. Okay. Anyways, so now I was a good citizen here and said, okay, I'm in Sweden. But actually, when I move this laptop to some other country, it might be that I need to change this. Anyways, the RSSI is the receive power. So this is the receive power. And that is the power I'm receiving at this moment. And it's minus 75 dBm. So 0 dBm is 1 milliwatt. Okay, so the receive power here is 10 to the minus 7.5 times 1 milliwatt. Ten to the minus 9, say, watts. That's not a whole lot of power, right? So the receive power is very weak here. The noise level, luckily, is even weaker. It's at 90 dBm. So the difference between these two things is the signal to noise ratio, which in this case is what? 90 minus 75, that's 15 dB, right? So the receive power is 15 dB. The useful signal is 15 dB higher than the noise power. Okay. Then it was deemed, my laptop has decided that this will allow the laptop to transmit data with 59 megabits per second using this physical mode and this modulation encoding scheme. Okay, so we'll look into this in a second, right? But if the SNR is higher here, we can probably transmit with a higher power, with a higher data rate. If it's lower, then definitely we need to go lower here. Okay, so the data rate you get out of your laptop using Wi-Fi very much depends on how close you are to the access point. That's one thing. And the second thing it depends on is how many are using that access point at the same time. So when you go to the train station and you try to use EduRoam, it's like, it takes forever, right? I mean, it's super slow. While at home or here in the office, it's pretty good. I mean, I don't know, EduRoam, you probably don't have that at home, or maybe you do, but it could be better or worse. Okay, so this is how, give me 5 minutes and I will just explain this. So this is how typically how data is transmitted. It's using something called orthogonal frequency division, where each of these lines here is a subcarrier. So we have frequency on this axis and time on this axis. Everything which is green here is data. The blue things here are to measure the channel. The white things are not used. Okay. I won't go into super much detail here, but typically here for a very common setup here is where this is approximately 20 megahertz. Okay. But it could be also 40 in some cases, sometimes 80. Okay, and then this modulation and coding parameters. We have different modulation formats here. If you remember in the beginning of the course, we had this BPSK, QPSK, and QAM constellations. And then there is some error control code rate on this. And then one, there's a much blah, blah, blah here. But basically here we see the different data rates we can get. So we get different data rates depending on which coding and coding and modulation scheme we have used. And there is another table from the standard actually pointing out this modulation coding index 6. This modulation coding index 6 that indicates that we are using 64 QAM with a 3/4 error control, with a rate 3/4 error control code. And it gives a data rate of 58.5, which my laptop optimistically told me was 59 megabits per second. Right? Yes, and this for sure was over. There, I did not write down all the data here, but also, yeah, anyways, this is what it is. I think we should finish now, because I took 5 minutes of your break anyways. So next time, so there is no lecture on Thursday. So this week is a lot oral exams and whatnot. So we will see each other next Monday, and then we will talk about network security, which will be the final lecture with some new material, and then there will be a review lecture, and that's it for the course. All right. So see you in a week.